Hello, this is John Wallace, Senior Editor at Laser Focus World, and welcome to today's webcast brought to you by Laser Focus World Online. First, I'd like to thank Hamamatsu Corporation, the sponsor of today's event. The event, titled Low Light Detection, Photomultiplier Tube versus Silicon Photomultiplier, will be presented by Slawomir Piatek, a physicist at Hamamatsu. Following the talk, we'll have a short question and answer session. Before we begin, I'd like to cover a few housekeeping items. At the bottom of your audience console are multiple application widgets you can use. If you have any questions during the webcast, you can click on the Q&A widget and submit your question. We'll try to answer these questions during the live Q&A portion at the end of this webcast, and please do submit questions. We encourage it. You can expand the slide area by clicking on the Maximize icon on the top right of the slide area, or by dragging the bottom right corner to enlarge. In fact, you can expand and reposition many of the components on your screen, so please feel free to arrange as you wish to give you the best webcast viewing experience. If you have any technical difficulty during the webcast, please click on the Help widget. It has a question mark icon and addresses common technical issues. If you still need assistance, just type your issue into the Q&A widget, and a member of our webcast support team will work with you to correct the problem. I'd like to note that we also have a few relevant online polling questions for you to answer, which are placed throughout the webcast, and you'll just be clicking on the button to answer each one of them. For your convenience, this presentation will be available on demand within 24 hours of this live event. A reminder email message will be sent to all registrants with a link to the archive. It will also be accessible from the homepage at www.laserfocusworld.com. Now it gives me great pleasure to introduce today's speaker, Slawomir Piatek.
Thank you. I can go. Good afternoon and good morning, everyone, depending where you are. And thank you for logging into this webinar. We're going to discuss two fascinating photodetectors, Photomultiplier tube and silicon photomultiplier. Even though they represent completely different technologies, there's something in common to them, and that is very high, on the order of million or so, internal gain. This high internal gain allows these two detectors to detect even individual photons. Not long ago, maybe 20 years ago, Photomultiplier tube was the only detector with this capability. With the development of silicon photomultiplier, now we have two, and sometimes the choice of detector for an application can be, let's say, difficult to make.
This is John, the moderator. We would like to do one of our polling questions now. This is the first of, I think, 4 questions. Very simple, just click on yes or no. The question is, before today, were you aware that Hamamatsu manufactured silicon photomultipliers? And just answer. We'll take about 10 or 15 seconds to answer that. Then we will continue with the webcast. Okay, that's a good length of time. Now, Slawomir, you can continue. Thank you.
Thank you. The webinar is organized as follows. So first, I'm going to spend a few minutes discussing the family of PMTs and silicon photomultipliers, discuss their structure, basic principles of operation. After that, we'll discuss, there'll be a side-by-side comparison of their major opto-electronic properties. And the presentation is going to finish with examples of some applications, three in particular, where one could choose between PMT and SIPM. Welcome to a PMT family. On this slide, on the left picture here, we see many members of this photodetector family. PMT is called a vacuum tube technology. It comes in great variety of sizes, ranging from several inches across the photocathode, which is a part of it sensitive to light, to inch or less. There are two major architectures of PMTs, head-on which I'm pointing now, and psi down. Silicon photomultiplier, or SIPM for short, is a pixelated device. It consists of pixels, which I rather would like to call microcells. The device has two prongs, anode and cathode, similar names as for diodes, though this is not a diode. Also, I would like to stress that silicon photomultiplier is not an imaging device. One cannot capture scenes with this device. It is a point detector, just like PMT. The number of microcells varies from about a few hundreds to several tens of thousands. Here we see a basic structure of the PMT. Every PMT is going to contain these three, or perhaps four, major elements. First, is the photocathode. It's the part where energy of light is converted to a photoelectron. The second part are focusing electrodes, which shape electric fields inside of PMT so that these produced photoelectrons in the photocathode can reach the first dynode. Thus, dynode is the third major component of the PMT. At the dynode, the process of multiplication occurs. The final major component is an anode. Anode withdraws electrons to the outside world, where then the resulting current can be sampled by subsequent electronics. As I mentioned before, PMT is a vacuum tube, and therefore, in this glass enclosure, one would hope one has ideal vacuum. Silicon photomultiplier is a solid-state device. Each microcell consists of two devices, avalanche photodiode and quenching resistor. In general, avalanche photodiode can operate in two regimes. The first one is called linear, and the second, Geiger mode. In the linear mode, an avalanche that is triggered quenches by itself. Typical gains in that mode are on the order of 10, 20, up to about 100 or so. In Geiger mode, the gain can reach values of million or so. In Geiger mode, the avalanches do not quench by themselves. They have to be quenched externally, and this will be a role of the quenching resistor. On the left-hand side, we see a top view of one microcell. This wiggly structure is the quenching resistor, which sits on top of its silicon oxide, an insulator, which insulates the APD structure below. Here we see a vertical cross-section of a silicon photomultiplier. RQ in red is on the top, insulating barrier, silicon oxide, and then we have essentially a PN structure. The heart of SIPM, or a single microcell, is a high field region where Geiger discharges occur. As I mentioned before, all microcells are connected in parallel. Thus, the device has only two output prongs, an anode and cathode. Let us briefly discuss the basic principle of operation of a PMT. First, all components in a PMT, photocathode, diodes, and anode, must have electric potential applied to them. This is done so in the simplest way by using a resistive voltage divider. Across the divider, we connect the voltage source, typically for a PMT on the order of 1,000 or so volts, 1,000, 1,500, at that order. The electric potential increases from cathode upstream. In typical application, anode is at the ground potential and the cathode at the most negative potential. A photon comes in, it strikes the photocathode, and if the photon's energy is higher than the work function of the photocathode material, an electron can be emitted. This follows the famous photoelectric effect. The focusing electrodes and the existing electric field inside of the PMT steers this electron towards the first dynode. As the electron moves towards the dynode, it gains kinetic energy, reaching about 100 electron volts or so. It strikes the dynode, and in response, the dynode may emit some number of electrons, 2, 3, 4, typically on that order. This process is known as secondary electron gain or emission. And delta describes how many secondary electrons are emitted. This process is repeated as many times as there are dynodes. There are PMTs with 9 dynodes, 10, 12, even 12. As we multiply the number of electrons, by the time they reach the anode, the collecting element, from 1 electron, we can have now 1 million or so. Electrons move out of the PMT, are sampled by electronics. Electrically speaking, a PMT is a current source. It produces current pulses. One can show that the gain, which is a ratio of anode current to cathode current, can be expressed as a product of deltas, individual deltas, for the dynodes. One can further show that under some assumptions, this gain is proportional to A, which is a constant that is unique to a PMT, V, the supply voltage, K is another constant on the order of unity, and N, a number of dynodes. On the right-hand side, we see a typical pulse coming out of a PMT. Let's now briefly review the operation of SIPM. As mentioned before, a single microcell is a series combination of avalanche photodiode and a quenching resistor. The entire device is biased with a bias voltage which is typically on the order of a few tenths of volts. The bias voltage must be high enough so that it exceeds the breakdown voltage of an APD. The breakdown voltage is the dividing voltage between the linear mode, where the gain is on the order of 10 up to 100, and Geiger mode, where the gain can be million or so. Typically, we exceed the breakdown voltage by a few volts, 2, 3, 4, or so. A photon comes in, it's absorbed, and it produces electron-hole pair. Depending on the design of the device, either one of them, either hole or electron, enters the high energy or high field region of a depletion region and triggers an avalanche. This avalanche grows. However, as I will show in the next slide, it will be eventually and rather quickly quenched by the quenching resistor. After quenching, the APD will be recovering back to its light-ready state. Since photomultiplier tube, since silicon photomultiplier is such a new device, I would like to spend a little bit more time discussing its operation. This is a basic model. We're going to model SIPM with this electrical circuit. First, a junction capacitance, or this capacitor here. It represents the capacitance of the depletion region in SIPM. RD, which is the resistance of depletion region during avalanche. This resistance is typically small, on the order of a few hundred ohms. Then we have a voltage source VBD, where VBD stands for breakdown voltage. Again, this is a model. There are no real voltage sources inside of SIPM. This is how we model its operation. And then there is a switch, on-off switch. I'll describe its role shortly. Externally to SIPM microcell, we have a quenching resistor. As mentioned before, its role will be to quench the avalanche. And an external bias voltage. In a ready state, the switch is open, and the bias voltage is above breakdown voltage by a few volts. That voltage we call overvoltage. The junction capacitance is fully charged to the voltage V bias. When photon comes in and triggers the avalanche, the switch closes. I should have mentioned that the value of the quenching resistor is typically on the order of hundreds of kiloohms, much, much, much larger than the value of RD. Thus, when the avalanche is triggered, the switch S closes and the capacitor begins to discharge. It has two paths to discharge, but it's going to choose this path because this is the path of lower resistance, and of course VBD is less than V bias. The discharge current, which is shown in red, is not accessible to us. This is internal current. However, as the discharge continues, the voltage or the potential at this point drops, and thus a current shown in blue begins to flow through the quenching resistor. This is the current that we observe, and on the right-hand side we see its dependence as a function of time. So as this potential drops, the current increases. However, when this potential drops to about VBD, then the avalanche quenches, it stops. There's not enough electric field in the high field region to sustain the Geiger discharge. We reach a peak. At this point, the switch opens and the capacitor begins to recharge with a time constant, which is about RQ times Cj, much longer than the time constant associated with the leading edge. This time, from Tmax onwards, we call recovery time. Some people refer to this as dead time, but this is somewhat incorrect. A microcell can re-trigger even during a recharge time. But the gain, of course, is the area under the curve, and one can show that the gain is equal to delta V, an overvoltage, times junction capacitance, divided by elementary charge. Let me summarize some basic or important points about the structure and operation of these two devices. First, to operate PMT, one requires voltages, supply voltages, on the order of 1,000 or so volts, tens of volts in case of SIPM. There are three major components of a PMT. In fact, every PMT will have these components. It's always dangerous to say always every, but here it is true. Every PMT will have a photocathode, some number of diodes, which incidentally come in a variety of shapes, geometrical shapes and designs, and anode. In case of SIPM, each SIPM consists of microcells. Each microcell is an avalanche photodiode in series with quenching resistor. And what's important is that these microcells are connected in parallel. I should have also mentioned or stated that SIPM is also a current pulse. So the output, we get current pulse, not the voltage pulse. Another important point, which I did not stress in this presentation, is that PMTs certainly can have very large active areas, but also very small output capacitance. The output capacitance is only a function of the anode and the last diode. So one can have several inches of photocathode and still very, very, very tiny capacitance. This is a very important property of a photodetector when it comes to high-speed detection. This is not so in case of SIPM. As one increases the active area, one will have to increase the capacitance, since Cj is proportional to the area, cross-sectional area of a PN junction. However, what one can also say about SIPMs is that the overvoltage delta V is a key parameter controlling various aspects of SIPM's operation. We'd like now to break for... Yes.
Yes, now it's time for our second poll question. And once again, in this case, you have multiple choice. So we'll ask you to click on the choice that you prefer. Question is, have you used PMTs or SIPMs previously? And the possible answers are PMT only, SIPM only, both, or neither. So we will take a few seconds for you to answer the question. All right, that should do it. Thank you.
Let us now discuss some basic opto-electronic properties of the two devices. Let's begin with probably the most important one, which is spectral sensitivity. On the left-hand side, we see a plot of spectral sensitivity of the PMT as a function of wavelength. To those that prefer quantum efficiency, those are shown with these diagonal contours. I'm now pointing at 50% quantum efficiency, 25, 10%, etc. We see many curves, and that is because for PMT, the quantum efficiency is a function of first, the glass material through which photons must go through before reaching the photocathode, and also on the type of the photocathode. There are a variety of materials used for photocathode. As a family, we see that the coverage spans from about UV, 150 or so nanometers, to about 1,700 or so nanometers. I should say that there is no single PMT that has this wide coverage. Quantum efficiency in the PMT does not depend on supply voltage. Again, it only depends on these two aspects, type of glass and photocathode material. In case of SIPMs, we do not talk about quantum efficiency as a measure of device response to light. Instead, we use so-called photodetection efficiency, which is a product of three parameters. The first one is the geometrical fill factor. So this quantity represents the actual area that is sensitive to light. The fill factors range from about 50 to more %. On one of the very first few slides, we showed that the quenching resistor is on the side where photons come from. And so that quenching resistor is going to certainly represent a barrier to photons trying to penetrate into the PN structure. The second parameter is quantum efficiency, which is the probability that a photon, once penetrated into the PN structure, actually produces electron-hole pair. And the final factor is avalanche probability. Just because a carrier injects itself into the high field region doesn't mean that avalanche is going to occur. Avalanche probability is a sensitive function of overvoltage. On the left-hand side, we see photon detection efficiency as a function of wavelength for three sample SIPMs produced by three major manufacturers, Sensol, Piatek, and Hamamatsu. We can see that PDEs can vary greatly from device to device. We also see that the spectral coverage ranges from about 300 or so to 900 or so. As of now, the spectral response of SIPM is limited by silicon. There are no SIPMs made of other semiconductor devices at this time. However, this is likely to change in the future. PDE is also a function of overvoltage. Here is a plot of PDE as a function of bias voltage, and thus overvoltage if we subtract from this the breakdown voltage. And one can see that the PDE increases, but eventually steadies itself as overvoltage is increased. Looking at the numbers, we see that PDE is on the order of 50, 60% or so. A little bit higher than for PMTs, where it turns out that theoretically one cannot exceed the 50% barrier. Let's summarize the spectral coverage of the two devices. There are different PMT offerings for spectral ranges from UV to IR. In fact, PMTs can be easily optimized and customized to cover the required ranges of electromagnetic radiation. QE only depends on the type of glass and photocathode material. And as I already said, sensitivity of a PMT can be tailored by different photocathode materials. This is not so for SIPM yet. However, for SIPM, we see that photon detection efficiency is a function of overvoltage. And as I already mentioned, it's limited to silicon. Let us now discuss gain. As mentioned before, the gain of PMT is proportional to supply voltage, to basically power n. So there is a power law dependence on gain and supply voltage. On the left-hand side, we see a plot of gain versus supply voltage for a very common PMT, R298. And we see that for the voltages supplied, the gain can vary from about 10 to 5 to over actually 10 to 7. In some cases, for some PMTs, the gain can even go to 10 to 9. The gain depends on the number of diodes. However, for a given PMT, one can actually change the number of diodes by shorting them. This is sometimes a good way to extend a dynamic range of the PMT to higher light levels. And the gain does not depend on the size of the photocathode. The gain of SIPM is given by overvoltage times junction capacitance divided by fundamental charge. On the left-hand side, we have a plot of gain versus overvoltage for 3 SIPMs that differ in the size of a microcell. For a given overvoltage, SIPM with largest microcell size has the largest gain, and that is because junction capacitance scales with size. What's rather remarkable about SIPM is that the gain does not depend on RQ. It also does not depend on temperature, provided, however, that overvoltage stays constant. If I do not ensure that, changing temperature actually greatly affects breakdown voltage. So if the supply voltage stays fixed, the gain would change. So as a practical matter, gain does not depend on temperature. Again, provided, that's a very important point, provided overvoltage is fixed. Varying gain for SIPMs is limited. If for a PMT, we can change gain by a factor of thousands, as a matter of fact. For SIPMs, maybe by a factor of 2, 3, or 4 or so. Let's summarize the key points. The gains of two detectors are comparable. The gain of a PMT depends primarily on number of diodes and supply voltage. The gain of a SIPM depends on the size of a microcell and overvoltage. For a given PMT, one can change gain by a factor of thousands. In case of SIPM, that variation is only by a factor of several. Let's now briefly discuss dynamic range and related concept of linearity. In case of PMT, linearity is a function of voltage divider, or more specifically, the current in the voltage divider. As a rule, practical rule of thumb, if the anode current does not exceed 1% of the divider current, then the PMT is satisfactorily linear. And here, on the left-hand side, we see a plot of deviation from linearity as a function of anode peak current. So this is the pulse operation, which is probably one of the most interesting regime. We see that linearity improves with increasing supply voltage. However, though not discussed in this webinar, there will be trade-offs. If one increases supply voltage, other forms of noise, which we'll discuss next, may become important, like cold emission from diodes. In case of SIPMs, linearity is limited by the number of microcells and duration of recovery time. On the plot, we see the output in some arbitrary unit as a function of input power. You may think of this as input number of photons. The ideal behavior is shown by this black dashed line. The actual behaviors are shown. And on the right-hand side, we see the number of microcells corresponding to those responses. Thus, SIPM with the greatest number of microcells remains most linear out of these four devices represented in the plot. In practical applications, it is highly advised that SIPM is equally illuminated or uniformly illuminated. If one spot illuminates a certain portion of SIPM, the dynamic range is going to go down. This is not so for PMTs. We've discussed good things, and now it's time to discuss some bad things, which is, of course, present in all photodetectors, and that is noise. The most important one are dark counts. So by dark count, we mean existence of output current poles, even if no light is present. In case of PMT, the main source of dark counts are thermally emitted electrons from the photocathode. Yes, there are also thermally emitted electrons from diodes, but those do not see the full gain. Electrons from photocathode do. Here is a plot of dark count rate as a function of temperature for various photocathode materials. We can see that these dark count rates can be quite small, on the order of just few electrons per second at room temperatures, as for example shown here, all the way to ones where you have millions of emitted photons per unit area per second. I've calculated dark count rate density for a typical PMT at 25 degrees Celsius. And here we see that one can have about 10 electrons per second per millimeter squared for this typical PMT. Admittedly, there are PMTs where the rate will be much higher and could be much lower if a PMT is cooled. But let's think of this as sort of typical or possible. In the next slide, we see now the corresponding count rates, dark count rates for SIPMs. There are two major differences. One is that dark count rate for SIPM is a function of overvoltage. In case of PMT, that's not the case. For the PMT, it's only a function of temperature. And like in PMTs, as shown on the diagram on the right-hand side, dark count rate will be a function of temperature as well. Here we see a plot of dark count rate density as a function of normalized overvoltage for several temperatures. And we clearly see that the dark count rate increases. Again, I calculated dark count rate density for a typical SIPM and found the rate to be about 56,000 electrons per second per millimeter squared. Now, this is much higher than what we obtained for a PMT. Another type of noise that can exist in a PMT is afterpulsing. On the diagram, which shows number of counts versus delay time, so these counts correspond to primary pulse, current pulse. And we see that primary current pulse can be followed by secondary pulses. We call them afterpulses. The main cause of afterpulsing in PMT is ion feedback and elastic scattering of electrons, primarily from the first diode. In many applications, this is not an issue. There is very little signal in afterpulsing. However, it can be an issue in applications that rely on, for example, coincidence measurement or timing measurement. There is a corresponding afterpulsing noise in SIPMs as well. So first, let's visually observe the afterpulses. This is oscilloscope screenshot. Oscilloscope was set in persistence. So this is the primary pulse. And we see that after the primary pulse, we have a forest of these secondary pulses, afterpulses. The physical picture is as follows. When a microcell is in a Geiger discharge, some charge can be trapped in lattice defects, for example. When a microcell is recovering, as I mentioned before, this is not a dead time. That microcell can be put back into Geiger mode because the field in the microcell is sufficiently large for this to happen. So if a charge is released by the charge trap, it can re-trigger an avalanche, though the afterpulse avalanche is going to contain less charge. The plot I was pointing to you is for quote-unquote old SIPM. By old, I mean 5, 6 years old. The modern 2015, 2016 SIPMs have almost no afterpulsing. The probability is extremely low, as shown on the graph on the right-hand side. For modern SIPM, at 25 degrees Celsius, for a typical overvoltage of 2-3 volts, we see that the afterpulsing probability is on the order of 1 or even less than 1%. One can almost state that afterpulsing is no issue for SIPMs anymore. Before moving on to applications, I'd like to discuss one more type of noise that exists in SIPMs but does not have a counterpart in PMTs, and that is optical crosstalk. So first, let's visually observe optical crosstalk on this screenshot from an oscilloscope. There's no light. The only pulses that we get are due to dark counts. If there were no optical crosstalk, we would only be getting one PE waveform. However, the plot clearly shows waveforms that are 2 PE, 3 PE, and more. This is known as crosstalk. The physics of crosstalk is as follows. During Geiger's discharge, hot plasma can emit photons that are capable of producing electron-hole pairs in silicon. There are about 30 of them per discharge. These photons go in all directions. However, some may go in the direction of neighboring pixels, create electron-hole pair, and one of these two carriers may inject itself into the high field region, creating a discharge there. Because crossing time of photons is very, very small. Photons, after all, move with the greatest speed. Those secondary discharges are simultaneous with the primary. That's crosstalk. On the right-hand side, we see a plot of probability of crosstalk as a function of overvoltage. And for a typical overvoltage of 2, 3 or so volts, we see that optical crosstalk is less than about 10%. The plot above I showed you is for old SIPM because I wanted to clearly see the crosstalk. Please note that for modern SIPM, the amount of crosstalk can be very small, as again indicated by the graph on the right-hand side. However, it is not likely that crosstalk will be driven all the way to zero. There was some improvement made, but ultimately we cannot completely optically isolate microcell from its neighborhood. So crosstalk probably is going to be a surviving type of noise in SIPM. Let's summarize noise for these two devices. Very importantly, the dark count rates in PMTs can be as low as just hundreds of counts per second per millimeter squared of the photocathode. Dark counts in SIPM can be very high, ranging on the order of hundreds, in some cases even thousands of counts, kilo per second per millimeter squared. For PMTs, dark count rate density, depends only on temperature, whereas for a SIPM, we have both temperature and overvoltage dependence. Let's now discuss timing properties. This is not a noise per se, but can sort of act as a noise or uncertainty in some measurements, timing measurements. So time resolution, or jitter, is the following. It's a variation in the transit time. Transit time is a time between the instant that a photon strikes a photocathode or surface of SIPM to the time when output current pulse reaches a maximum. If the world were ideal, this transit time would be the same each time a photon strikes the photocathode or SIPM. In this case, jitter would be equal to 0. However, the world is not ideal, and thus there will be variation in transit time. That variation is what we call jitter. And this property is very important in applications, again, that depend on timing, like LIDAR, for example, or PET. On the left-hand side, we see a plot for a PMT. The width of this plot represents the jitter, which is about 130 picoseconds or so. So typical PMT will have a jitter on this time order. Since PMTs can be optimized and customized, there are PMTs where jitter is much lower, on the order of just few tenths of picoseconds. But a typical PMT will have jitter on this scale. I should note that when jitter is reported, it is reported for single photon striking the photocathode material. So we call it single photon jitter. On the right-hand side, we see a plot of single photon jitter for SIPMs. The three curves represent different sizes. For typical overvoltage of 2 or 3 volts, we see the time jitter is on the order of 100 or so picoseconds, or even less, quite comparable to that of a PMT. For both devices, jitter is going to decrease in case of PMT, supply voltage; in case of SIPM, with overvoltage. Likewise, for both devices, jitter is going to decrease with number of photons. One can make therefore a statement that a jitter of a SIPM is quite comparable, perhaps even better, compared to a jitter of a typical off-the-shelf PMT. Of course, it's no match to specialized PMT for very small jitter. But if I, again, randomly pick two devices and compare the jitter, SIPM is very comparable, again, if not better. Since we have only 45 minutes to discuss these two fascinating devices, let me quickly compare some properties, remaining properties, in a tabular form. As always, red is going to represent minus or disadvantage, and green is going to show or represent advantage. PMTs are susceptible to magnetic field. Their performance can be affected greatly by the presence of the B field. However, remedies do exist. SIPMs are completely immune to magnetic field. PMTs can be fragile, after all, they're made of glass. However, ruggedized versions do exist. In fact, in oil logging, we use PMTs for the detection. SIPMs, because of solid-state technology, smaller size, are more resistant to shock and vibration. Radiation hardness of PMTs is excellent. It's very difficult to hurt PMT with beams of protons or neutrons or electrons. For SIPMs, it's good. However, there is still investigation ongoing. SIPM is a new device, and so there's still quite a bit of academic and industrial research into this issue. However, we do know that high neutron exposure can increase dark current in SIPMs. That's why the red marking for this device. Exposure to ambient light can damage permanently a PMT, especially if it's fully powered. In case of SIPM, no damage. Hysteresis, yes, for PMTs. Hysteresis refers to a situation where current operation of a device depends on its history of operation. It's kind of like a memory of what happened in the past. So yes, PMTs do have hysteresis to various degrees. SIPMs, none. Ease of gating, easy for PMTs, rather difficult for SIPMs. The cost for PMTs, well, it can be high or quite low. It depends. If I request a PMT that has 1 millimeter by 1 millimeter size, that will be very expensive because it's very difficult. PMTs are still, or some aspects of PMT are handmade. And so making such tiny PMT could be quite expensive. Not so for SIPMs. However, as I increase the size, the cost per unit area for PMTs is going to drop. So let's say I want a device that is 1 inch or 2 inches of active area. Choosing PMT will be much, much less expensive than choosing SIPMs. In this case, one would have to have a tile of SIPMs to give me such comparable aerial coverage. So I could summarize that as size increases, the price of a PMT drops, whereas the price of SIPM increases. It's now time for polling question number 3.
Yes, and the question itself is, in your situation, what are the most important parameters for the detector? And the possible answers are sensitivity, spectral response, speed, internal noise, operating voltage, or other. Now, Slawomir, do you know if this is if people can select more than one answer here?
No, just one.
Just one. Okay, so select one answer, and we will wait a few seconds for you to do that, and then we'll move on. All right, thank you, and we'll move on with the webcast.
Let us now discuss some applications where one would have to make a choice between SIPMs and PMT, and that's because all these applications, these 3 applications, involve very low light levels. One is bioluminescence, or a related idea of chemiluminescence. Suppose I have suppose I have a compound whose concentration I would like to detect. The concentration of compound is very low. One possibility is to put another compound, let's say compound B, which binds with my compound A, and as a result of binding, light is emitted. The emitted light is in all directions, therefore it's diffuse, and there's very little of it. The diffuse light and very sparse light are the application challenges. The photodetector considerations, therefore, would be highly desirable to have large active area at the low cost and high sensitivity and low noise. Let's briefly compare our 2 devices. Active area of a PMT, it can be very large. The cost, as we already discussed, larger the area, lower the cost per unit area. PMTs have quite high QE and very low dark current. So all greens for PMT. SIPMs via arrays can have large area, but as we discussed, cost increases as area increases. They do have high, they can have high sensitivity. However, the dark count rate is quite high. And so in this case, PMT would be a much better choice. LIDAR. The LIDAR, especially applied to self-driving vehicles, is a technique where I can measure distance to obstacles. Light is emitted, light that reflects from a target and detected by the detector. By timing the time of flight, one can gauge the distance. Some application challenges are as follows. Very intense ambient light. Cars are driven day and night. The range, we have to be able to detect distances, small, fraction of a meter, to perhaps many meters, or even fraction of a kilometer. We have to have a safe regime of electromagnetic radiation, so probably infrared. The devices should consume little power, should be resistant to vibrations, and the size should be small. And thus, the consideration for the photodetector as follows: should be immune to stray light, sensitive in infrared or near infrared, should be inexpensive, and most likely solid state. Not surprisingly, if we compare the two detectors side by side, there is more green in the column for SIPM than for PMT. Finally, let's discuss the third application, radiation measurement. There are two types of radiation measurements. The first one, we just are interested to know whether radiation is present or not. But what do I mean by radiation? By radiation, I mean particles, like alpha particles, beta particles, gamma rays, protons, neutrons, electrons, that a photodetector directly cannot detect. In this case, we use scintillator. What happens is that the radiation particle is absorbed by the scintillator, where its energy is converted to light that the photodetector can detect. The scintillator acts like a proxy, or like a converter of radiation's energy into energy in form of light that the detector can detect. And so, due to security reasons, we'd like to monitor radiation, for example, in trucks, ships, airplanes. And so some challenges are sensitivity. Our detector should be capable of detecting even low doses of radiation. Therefore, a photodetector consideration is a large active area. We'd like to scoop as many photons as possible from this sparse radiation field. And the cost, of course, should be small. Another type of radiation measurement is when we are actually interested what the radiation is, whether it's alpha particle or beta or whatnot. So identification is necessary. To do so, we typically construct energy spectra, and thus the energy spectrum should have high resolution, which is going to mean a detector with high sensitivity. These detectors should be small because we are interested in devices that are handheld, as shown on the right-hand side. And thus, there should be small power consumption, low cost, and low size. And this probably favors, therefore, a solid-state device like silicon photomultiplier. Comparing the two, for radiation monitoring, we see green for PMT. So in this case, PMT is probably a better choice, again, because of its large active area and low cost as area increases. For energy resolution, we see more green, in fact, all green in case of SIPMs. High photodetection efficiency, compact, low cost, and low operating voltages. Finally, or next to finally, there's a quick comparison table between the two devices. There are several entries. I'm just going to point. Those are the outlined in color. Bias voltage for PMTs, 1,000 volt or so. For SIPM, 60 or so. Dark output for PMTs can be low. For SIPMs, high. Magnetic field, PMT needs protection. SIPM immune. Temperature sensitivity for PMTs is quite low. For SIPMs, medium. Again, if one wants constant gain, overvoltage must be kept constant because breakdown voltage is a function of temperature. Ambient light can damage PMT, no damage to SIPMs. We've reached summary and conclusions. I would like to just point out a couple of the few from the list. One is that advantages of SIPMs are low cost, low voltage operation, magnetic immunity, and durability. Advantages of PMTs are high gain, very low noise, wide spectral coverage, large area, and more. And the other item I would like to underscore is that choosing between these two devices can be actually quite complex process. And therefore, we highly recommend that potential users do contact experts, which in this case would be the manufacturers. And that expertise can help quickly build the devices that a customer or potential user is investigating. Thank you for listening. Thank you very much. I would like to just mention that there are some upcoming presentations on SIPMs given by me. There will be 3 of them at Photonics West. How to select the right detector for your application, silicon photomultiplier theory and practice, and single photon detection, SIPMs versus PMTs. This will be a longer version, 8-hour version of this webinar. At the bottom is my contact information. Again, thank you very much, everyone, for attending and listening. Thank you.
Thank you, Slawomir. It's now time for Q&A. But first, we have one more poll question, and this poll has a different purpose. We just want to know who wants to get a PDF of today's presentation and who doesn't. So if you click yes, you'll get a PDF. If you click no, then you won't. I will just take 5 seconds for you to click yes or no, and then we'll move on to the Q&A. All right, we have limited time, so I will ask about 3 or 4 questions. First question: can PMTs and SIPMs operate in the IR region?
So that's right. So the response of SIPM is limited by silicon. So the current family of SIPMs has sensitivity up to about 900 nanometers, which is near infrared. In case of PMTs, the range is much larger on the red side, extending all the way to about 1,700 nanometers. Those PMTs, however, need cooling since dark count rates there would be much higher because, of course, the barrier, the energy barrier for the photocathode is much, much lower. Therefore, dark electrons can easily escape from the photocathode.
All right, and before I ask the next 3 questions, I do want to mention to the audience that any questions that aren't answered will be sent to the presenter, and he will be able to answer them later at his leisure. So another question, is temperature compensation necessary?
Yes, for SIPMs, that is correct. The reason for that is that breakdown voltage is a very sensitive function of temperature. So if I keep bias voltage fixed and temperature changes, the breakdown voltage changes, and that changes over voltage, leading to either higher or lower gain, depending in which direction the temperature has changed. And so in temperature changing environments, it's highly advisable that there is a feedback circuit that will stabilize overvoltage against temperature changes.
Okay, here's an interesting question. Do you foresee PMTs becoming obsolete?
I do not. The example of bioluminescence and chemiluminescence is a situation where PMTs cruelly outperform SIPMs. The large active area, the low output capacitance, which I did not stress in this webinar, and very low dark currents are simply superior for applications of this nature.
And last question for today. Are there any journal articles that compare the performance of SIPMs by different vendors?
Yes. In fact, we live in sort of golden age of SIPM. They've been developed in the 90s, and so approximately there are a few hundred articles on SIPMs per year. Not as many for PMTs because this is a more established technology. So absolutely. For example, some of the plots I showed in this presentation are from OTE 2016, which indeed compares SIPMs produced by different manufacturers. I should note that many of these articles come from academia, so there are unbiased assessments of the performance. I again highly recommend the very recent one by OTE 2016.
Well, thank you, Slawomir. Do you have any closing remarks?
Well, again, I would like to thank everyone to attend. Perhaps I should also mention that Hamamatsu is planning another webinar in January, if I remember correctly, January 15th, which will solely focus on silicon photomultiplier.
All right. Well, on behalf of Laser Focus World and Penwell Corporation, I would like to thank Slawomir Piatek of Hamamatsu Corporation for today's presentation, Low Light Detection, PMT versus SPIM. This presentation will be archived within 24 hours and can be accessed from the homepage at www.laserfocusworld.com. A reminder email message for the archive will be sent to registrants complete with a link to the archive. We thank you for joining us today and look forward to future webcasts.
Thank you.